Recording. Yeah, we're good. I assume you got that under control.
According to me, yeah, there's some.
That's fine.
Yeah.
All right. So this work is what I've been working on for the last year or so. Provocatively called "Where the Mirror Really Is," and I say provocatively because the margin means a lot of different things to a lot of different people. But using the radar, we think we can, for the first time, really get a daily view of the penetration of waves into the Antarctic. So I probably don't even need to mention this slide here, but the mud, a region of complex air, sea ice, ocean interaction. Now, the textbook technical definition of the MIS is the region of sea ice impacted by its proximity to the open ocean. And it's not any more descriptive than that, which kind of defined it. And so that can mean a lot of different things to different people, as I mentioned. For people, it's where waves penetrate into the ice. From Alison Cahoot's 2014 Nature paper and others in the field quite far into the ice. You can see my mouse. Yeah, so 1,000 kilometers into the ice is not really out of the question when the tide at the ice edge is very high. We're talking 12, 13 or more. Can get even higher than this in the Southern Ocean, of course. The attention into the pack depends probably a lot on the physical properties of the thickness, flow size, etc. But yes, many hundreds of their energy is fully attenuated, and as Mike knows very well, we don't exactly goes, but it goes somewhere, and eventually most of these waves get penetrated to the edge of the continent. But unfortunately, we have a widely used definition of the marginal ice zone, which can relate to this physical definition. So the marginal ice zone, from a remote sensing point of view, is defined as where the concentration is between 15 and 80%. And on the next slide, I point out all the problems with this. I think recently there's become even more widespread agreement that the 15 concentration doesn't necessarily equate to regions of ice by their proximity to the ocean. So, for example, the Massam 2008 paper. So these are two maps of sea ice concentration weeks. On the left, we have quite a diffuse ice edge in the Amundsen Sea. We see all of this diffuse ice edge has been compacted up against the coast due to a northerly wind. And of course, when we have a northerly wind, we've got a large fetch of the sun, which can generate large waves and swell. And so all of those large waves and swell are probably compressing this pack ice up against the coast, consolidating it, but also impeding. So we've probably got very high wave heights within here. However, if we were into 80% definition of the MIS, then we would say that this is not marginalized much sense at all. Another example of this is from Albert's Nature Communications paper last year, which showed the presence of wave trading into regions of 100% sea ice concentration. So can penetrate well into 100% sea ice concentration. And so this remote sensing of convenience is not a very good one. That's my argument here. Now I ask you all to cast your minds back to 1984. One thing happened in 1984. This great paper by Chris Rapley was entitled First Observations of the Interaction of Ocean Swell with satellite radar altimeter data. Now, in that paper, he used which was able to retrieve open wave height. So this solid line here is significant wave height in the open ocean. This satellite then encountered the ice edge, and then the wave heights steadily dropped to 0. And he called this region in between the ice edge and where significant wave height, called this the extent of the marginal ice zone. So this is the kind of maps that he was able to produce. So every 3 days from this rate to produce these circumantarctic maps. The black ring around Antarctica corresponds to this blue box here, the marginal ice zone, as seen by the radar altimeter. And you can see that the regions with a deep marginal ice zone correspond with region heights in the Southern Ocean. So this kind of makes sense. Genuine of wave penetration into the Antarctic sea ice. Why haven't we been able to do this since then? We've had far better radar. Reason why we couldn't have kept this kind of measurement going. And that's kind of the impetus doing lately. That's Tom Cruise. He was also released in 1984. Now, work by my fantastic honours student, Jill Brower, which was published in 2022, used satellite laser altimetry to determine of the wave penetration into Antarctic sea ice. So ISAT-2 as the polar orbiting photon counting laser altimeter. It's got a 17-meter, and this is easily able to resolve the wavelengths that we care about. So we're talking about meter wavelengths. Basically, the product work had segments of about 15 meters. So every 15 meters, we get a new height segment that we were easily able to resolve the wave passage. So this is what one of those ISAT-2 tracks looks like. So on the left-hand and on the right-hand side, we have the consolidated thick ice. This is the same track that's shown up here. Now, in the first about of this track, in the outer 180 kilometers, we see this characteristic triangular height. And so what this is waves which cause the ice surface to go both above the local geoid for that period of time. And this is characteristic into the interior of the ice pack here. So unarguably exactly where waves were penetrating at this particular region on this, like the gold standard of knowing exactly where the waves were fully attenuated. And Jill was able to do this for, I think it was about 400 or 500 tracks in the year of 2019. And what we see here in the blue numbers from this technique, and you can see that according to this, the seasonality of wave penetration into the MERS peaks in about a minimum in the summertime months. And if we compare that to the sea ice definition, you can see that it's far deeper than the sea ice concentration, about 6 times deeper, I think it ended up being in that paper. The problem with laser altimetry is we can't see through clouds with lasers, and it looked like this with big gaps due to cloud cover. A lot of tracks look to hold well. In the end, Jill was probably able to process about 10% of the tracks, as we just had to throw away because of clouds. So this wasn't really the all data set that we kind of hoped for because of the cloud cover, but it was still detailed look into attenuation along satellite tracks that we've. One of the upshots of this is Jill's dataset is probably like this, where we have very obvious wave attenuation. And she was probably missing cases marginal ice zone was quite thin because of the manual steps she needed to incorporate facts. So we think Jill's dataset may be a slight overestimation of widths. So the way forward from using laser to go back to radar altimetry techniques. The good thing about radar, of course, is it can go right through. And they use radars for determining wave in the ocean. And the way that this works is if you have a calm open ocean, as depicted in this, a lot of the radar return occurs in time because this surface is quite flat. And so we get this characteristic edge to our returned radar waveform. Whereas on the other hand, if we have a rough surface depicted in this bottom panel here, the radar energy intercepts the surface a variety of different times. In the end, we get a much gentler leading edge form. And this works in sea ice as well. So this is a figure from the Rapley paper, and it's the same kind of idea for a wave covered leading slope. And when we get a region which has no waves, we get a very warm and very steep leading edge. So this is the idea to a modern altimeter. So now we're looking at a new altimeter called Antarctic 2013. Basically, what we see here is stacked images of these waves. Is the open ocean, and this particular track goes into Antarctic here. What we see is a transition from an open ocean style waveform, which looks shallow leading edge like this. As soon as we hit the ice edge, we start seeing attenuation and eventually kind of situation here. This is the inner limit of wave penetration, where all of it comes from just one or two different range bins. And so by doing that, we can study the penetration of waves, and that's plus versus the significant wave height, which is here on the x-axis. This kind of general group of points here. So for increasing wave height, we tend to get penetration in this kind of region. And this makes a lot of sense. I'm not too worried about these points here on the right. So these are points where we have experiments that don't necessarily correspond with increased wave penetration. Is okay because we haven't taken wave direction or swell direction into account here. Northward or eastward propagating waves, which would not really penetrate into the sea. I tried to make these Rapley style maps, so of sea ice wave penetration around Antarctica, and it seemed to work fairly well with these, and I'll explain why in a minute. But here what I've done is just taken this of the wave or swell. So when we have a blue color, we have a southward component of the wave. The southward areas with a southward component tend to have larger widths, as depicted by these tracks here. So this kind of makes sense, but I don't think this is a good, because waves tend to decorrelate on much shorter timescales than 3 days. So we think hours based on wave buoy measurements. What I did though is I took the same month as shown in Jill's work and calculated the same box plot from the Altica radar altimeter data than what Jill had, and that's because I don't have these cloud limitations that Jill has. So, picture, and as suspected, we find that our median wave penetration is than what was reported in Jill's paper. So this kind of is exactly what we expect. Values are pretty similar, and this gives us confidence in the radar altimeter numbers. And this work is also backed up by the work of Noah, who's here in the room with me. Hi. So Noah has been running a sea ice wave interaction model at a 1/4 degree resolution. Stop me anytime I get it wrong, Noah. running for the same month of the year, but a different year. This is before NOAA had run 2019. Pretty much the same grouping of points and also the same kind of slope as this line. So this gives us some confidence in the results from the radar altimeter. Now this figure gives us even more confidence because what we have here in the red line is the number of the altimeter, and the blue line is NOAA's numbers from his ice ocean. And so we get almost identical seasonality and also it's from NOAA's model and from the satellites. So this is really our first seasonality of wave penetration into Antarctic sea ice. And it's made what we expected because going back to the sea ice concentration base definition, summertime, and it's a very large peak. Whereas we see actually it's minimum in the summertime or the late summer. I think it's quite a reasonable result given that we are starting to really trust these numbers from the radar altimeter. One thing we expect, if everything I say is true, we expect that we'll be able to see passage of storm systems from west to east in the Southern Ocean and the effect on wave penetration in the ice. And we can actually see that. You see all of this structure, which is diagonally aligned with this line that I've put on here. These storm systems propagate from west to east, and we do see upstream of these storms, we see the largest wave penetration. We can actually load up great visualizations such as this null school thing, and the date and time of this simulation just using the URL, and you can actually track these west to east as they propagate around the continent, bringing higher wave heights and higher ice penetration on their upstream eastern side. It's quite fun to do. Now, I want to talk a little bit about the seasonality of the result we're getting. So as you've seen in my results, we get a minimum in around February and a maximum in around September. And I wanted to talk a little bit about why we get that kind of seasonality. So what I've plotted here, thanks to Ian Young, who provided these figures for me, heights in February, in June, and in September, based on over the Southern Ocean. There's a couple of things going on here. The first thing is that the change in the wave height itself from February to June and then the maximum. That's one thing. The other thing that we've got going on is the location of the ice a lot from February to September, of course. And we get the ice edge pushed north in September, being the month of maximum extent, into this band of high. So this seasonality is probably a result of both this of storminess itself, plus the location of the ice edge. And there's also a third factor in here. We know from observations that ice thickness is maximized in summer, which is, but it makes sense if you think about it. So in September, we've got the ice furthest north, the region of the highest wave heights, and it's also the thinnest ice because September has pancakes. All of these things add up to us having higher wave penetration. So I wanted to also show a little first look at the ability. So this is just showing the years 2019 to 2022. Really rich data set. So there's a lot of interannual variability. Something crazy went on in August of 2022, and I wonder if this had something to do with the crazy sea ice seasonality that happened at around the same time, where the really huge retreat off. And that brings me to, so the take-home messages is I think we're in a new era of being able to altimetrically determine the wave-affected marginal ice zone. This new data set is super rich, and I think it will be really useful for of wave-ice interaction. And this new data set will be released pretty final touches on the first paper from this now. The seasonality has a winter time, a new result, and something that you certainly don't see if you use a concentration-based. So we can see waves penetration on pretty much a daily basis, but what about the marginal ice zone? So there's a lot of arguments about this. Like if we see waves penetrating 500 kilometers on one day, does this mean that the outer 500 kilometers of the pack ice is the MIS now? Or do we need 500 kilometer wave penetration events? What magnitude of wave needed to break flows and that kind of thing? These are still unanswered questions. Everything I've shown today is just the extent of the marginal ice zone, but using this table to determine the wave height all the way from the ice edge to the inner limit of, all we can see is where that inner boundary is. So we need higher resolution rate question, and collaborator Ximing Zhu and Weixin Zhu, this from Cryosat-2 and Sentinel-3. And I'm happy to take questions if you have any. Thanks, Mike.
Thank you very much, Alex. That was awesome, and you kept perfectly to time. Incredible achievement. All right, so questions for Alex. But I should have mentioned this. If people want to write the question, well, if, that's all right. I'm hoping someone else will ask another question. What about one of those people in the room there? With them to, they're all experts on it.
So you mentioned that having potential of significant wave height cutoff. What would be the reason?
I don't know if you could.
Alex, could you repeat the question?
I can repeat that. So Nathan asked why on the inner limit of the marginal ice zone, why can't we just set it to 0? Okay, so from the altimeter point of view, we don't actually know what that value is. We don't know subtle wave that can be distinguished apart from 0. View, we're not at the position to quantify the wave height at all. In NOAA's model, a cutoff of 5 centimeters, and that gives us what we see from the radar altimeter, but we don't know. Yeah, we think that the seasonality won't change no matter what threshold we use. It will just be that will change there. Yep.
Does anyone else have a question they want to ask? So I've got a few questions, Alex, and if no one else is going to ask them, you're going to have to.
Go for it.
What do you? Okay, why the heck did this thing come out and never get continued on? He got this paper in Nature, and that was it, or? That's
right. Certainly continued on. He went on to lead the British Antarctic Survey.
Yeah.
And he actually, I asked him to find the original data set, which is long to the sands and the magnetic tapes of time, that they actually found, and trying to get that data read back again. But yeah, it's only got questions or something. And Chris Horvat was the one who kind of guided and said, hey, we should try.
So it's actually likely to be it's very science work back in the pre-Google Scholar days.
Exactly.
Yeah. So, yeah, because it's very hard for, I can remember back to those times, would pull a paper out of his drawer and hand it to you. That was how you found a paper, because it was.
Yeah.
And then they fall off literally off the radar, as they'd say.
And Chris himself was kind of surprised at the increased traction this has got in the years. So Yeah, it's having
Yeah.
resurgence.
Well, because one of my, yeah, well, I'll ask my last question. I'm curious about what is ground truth, because here that picture you've got that maybe is the punchline of your talk, if you could just show us that one that compares the two curves, yours and Noah, yeah, that model there. And to my mind, the ground truth is not the model,
That's
especially
right,
when I see
yeah.
my part of it. But it certainly validates. So the ground truth is really
I'm pitching it as a cross comparison, this one.
yeah.
The validation has to come from ISAT2. We can't even use buoys for validation. Buoys are wave height, but we can't retrieve wave height. So it has to be ISAT2.
Yeah. But this is interesting that it does seem to point out that that model's working. Thinking.
No, it's smiling.
My model.
This is the Malin attenuation. Yeah.
Anyway, let's have a look at the questions.
You mentioned at the end using these data sets to calibrate wave models. What are the challenges of calculating attenuation rates given the timescales captured by altimetry? Information do you need to use? Really good question. So my who I mentioned on the last slide, he's been doing a lot of work in the Arctic. So he's taken the incident height and the zero from the inner limit of marginalized zone, calculated rate just based on those two. And I think there's probably some pitfalls of doing it that way. For Luke Bennett's has done work showing that as soon as you encounter, you get an amplitude drop. So you can't necessarily use the open ocean wave height or incident wave height, because you've got an amplitude drop and then you've got attenuation on top of that. Super tricky. I think we can use something like Jill's ISAT2 work to study. And Joey Vorman's is doing that from Jill's results as we speak. But using radar altimetry, because we still can't get wave height quantitatively, it's super tricky from this kind of data set. What it is probably good for is tuning attenuation rates to match your MES width, which is kind of what Noah's done. Yeah. Thanks, Madison.
Yeah. I concur with the second comment there about a great talk and a great way to. All right. So we've got a few minutes. I guess last question. So okay, yeah, past your bedtime. Great, God knows we don't want you bedtime. All right. Yeah, that's a really interesting work, and I think we saw satellites coming on stream, but I'm just astounded by the idea that there's this paper that he seems to have got, and you managed to quantify that entire marginal ice zone that came out of 1984. Yeah, and interesting that it got published in Nature.
I know.
Remembers commenting to me that he's got 3 papers in Nature and only one of them got cited. It's on this vibration of icebergs that's been sort of largely unsighted. Bizarre. I think we've, there's such a different age. On a lot from the. All right, thank you very much, Alex. So I'll just get everyone to thank you for your talk.